עם הקלטה או בלי הקלטה.
Okay, let's get started. There are not too many people here this morning. Hopefully people join us. And maybe people are watching the recording. Oh, here we go. More people are joining. So I'll wait one more minute to let people join. All right, let's get started. So I'll remind you where we were, and we put a measure on the space of lattices. So reminder, xn, which means Sn R over Sn Z. This is the space of lattices of covolume 1 in Rn. This notation, M of xn, is the unique SNR invariant Borel probability measure on xn. So we proved that such an object exists and is unique. And so our interest now is in lattices which are chosen according to this measure, randomly according to this measure. And the reason, one of our reasons for being interested in it was we were interested in the lattice which maximizes the packing density among lattices, which means among all lattices of covolume 1, the length of its shortest non-zero vector is maximal. We know that such a lattice exists, but we have no idea about the length of the shortest vector. And the best bound that we have essentially comes from an averaging argument. So we know the expected value of the average value of the shortest lattice vector. And since we know the average value, we know that there exists at least one lattice where the actual length of the shortest lattice vector is at least the average. So this is kind of a very indirect way of understanding lattices, and it leads to the desire to understand better the distribution as a probability space of certain functions on the space of lattices. For example, suppose you knew that the length of the shortest vector, lambda 1, is not very spread close to the average, so that there are lattices for which this function, thought of as a random variable, takes a value which is much larger than the average. That's what we're interested in. We're interested in lattices for which lambda 1 is very large, as large as possible. So from the point of view of random variables, we're trying to understand how concentrated this random variable is around its mean. And so that's the sort of the next order of business, is to understand. So let me just write that down. We given a function, let's call it f, on the space of lattices, want to know the distribution of its values is f of L close to the average. This is average of f with respect to this probability measure for most L. So that's kind of a question what we want to know, and specifically we want to know this for f, which is a Siegel transform of a function f on Rn. For example, F could be the indicator of a ball. This is the type of function that we were analyzing in order to understand we were computing the average of this type of function in order to understand the shortest lattice vector problem. Let me remind you what the formula means and the formula that we have for the average. So recall f hat is a function on the space of lattices defined by the Ziegler summation formula, and it satisfies that it's in L1 whenever f is in L1 of Rn, and we have something which we call the Ziegler summation formula, the integral of f hat is the integral of f. And let's remember that this formula was called Ziegler summation formula number 2, and I'm closing the brackets for this reminder from last week. So again, this is our random variable that we want to understand. And this formula, the right-hand side of this formula, is the expectation of this random variable. And we'd like to know whether there are functions for which this random variable is larger, much larger, or much smaller than the average. And you recall if B is a ball and F is the indicator of B, and this function is 0 on some lattice, that means that B contains no non-zero lattice points. So that's a way of exhibiting lattices whose shortest non-zero vector is actually long. Okay, so this is our question. So when you have a random variable and you want to, so here, when you want to understand how its values are distributed around its average, the way to analyze this probabilistically is to talk about the higher moments. So question 1, can we compute higher moment thought in space of lattices with this R-Ziegler measure? So I'm going to remind you briefly what the higher moments are and how they're used in order to compute the concentration of a random variable around its average. So this is a kind of a recall if you know this, or recall if you don't know this. This is some basic facts from probability theory. So the average of a function is denoted. Let's call x maybe let's call x the random variable. That's kind of a typical notation. So this is just the expectation is just the integral with respect to this probability measure, and the kth moment, sometimes it's called the raw kth moment of x, is the expectation of x to the k. So this is the integral on our probability space of this function taken to the power k. And there's something called the centered kth moment. This is the centered kth moment is when you integrate you first center the random variable so that it has expectation 0, and then you take the kth power and look at its expectation. Okay, so it's the integral in these terms. So I'm just sort of doing obvious things here, but sort of useful to see both versions of these formulas. Okay, so by the Siegel summation formula, this object is the expectation of x if x is the is a Siegel transform of a function f. And so this is the centered kth moment. The centered second moment is called the variance. Denoted by VAR of x. And we write it as sigma squared. Sigma is the standard deviation. So these are just notations from probability theory and the kind of some basic inequalities in probability that we're going to be using. So the first thing is Markov inequality. Some people call this Markov, some people call this Chebyshev. I'm just gonna not get into the dispute by mentioning both names. And so I guess the history of it is that Markov was a student of Chebyshev, and Chebyshev sort of published this, wrote papers where this is used implicitly, and Markov made this more explicit, and then it was named after Markov, but later on people realized that it was actually due to Chebyshev, so something like that. So suppose we have a random variable which is non-negative, doesn't assume negative values. So in particular, in the case that we're interested in, if x is the Siegel transform of a function f, and f is something like the indicator of a ball, so f itself is non-negative, then f hat will also be non-negative. So this would be an example. So you have a non-negative random variable. And you have a parameter a bigger than 1. And you know that the expectation of x to the k is finite. So the kth raw moment in the terminology that I used earlier is finite. Suppose you can establish this, then the probability that x exceeds its expectation by a factor of a is less than the expectation, the kth moment, the kth raw moment divided by a times the expectation, quantity to the power k. So I guess sometimes when k is 1, this is called the Markov inequality, but anyway, the proofs are always the same, so it doesn't really matter. Sometimes people distinguish cases here and call some things after Chebyshev and some things after Markov. So let's look at this and see what it's telling us. So the expectation is the average value. We're increasing the expectation. So this is a value that's larger than the average, and the inequality is giving us an upper bound on this quantity. It's showing us that it's not likely that you go much higher than the average. Okay, and you see that the term in the numerator and the term on the denominator are not the same. This is the average of x to the k, and this is the average of x quantity to the power k. They're not the same, but in many applications, they're going to be close to each other. In particular, that's what's going to happen in our situation. So suppose that they are close to each other. Well, they're only exactly the same. Let me write that down. That's an important special case. They are the same if k is equal to 1. If a is equal to 1, both this term and this term are the expectation of x. And so let's write that as a special case. If k equals 1, we get this. But even if k is not equal to 1, in many applications, the numerator here, expectation of x to the k, and this term, expectation of x quantity to the k, are close to each other, and then the quotient becomes 1 over a to the k. So the bigger k is, in other words, the bigger the k is for which you have such an estimate, the better the statement from the probability, from the proposition. Okay, let's prove this. It's a very short proof. You think, I'm going to use the fact that x assumes non-negative values, and I'm going to estimate from below the expectation of x to the k. So x to the k, well, there's a certain probability that it's bigger than a to the k expectation of x quantity to the k. And when this happens, the value is at least this. So this is obvious, right? I mean, the we're taking the average of x to the k. X to the k is non-negative. So what I'm doing here is I'm dividing the probability space into two cases. Either x to the k achieves this value here or larger. So then I multiply the probability that that happens by that value. So and so that I'm because this is a lower bound, I'm underestimating the contribution of this set of cases to the expectation. And then everything else, when the reverse inequality holds, I'm bounding from below by 0 because the random variable is 0. Okay? So this is a simple bound. And then the left-hand term, I can just divide through by, take the kth power, take the kth root, I'm sorry, and I get this way. And then I take, moving the terms over, I get the proposition. Okay. So this is, let's see, this is, if I move this over to the other side, I get that this is less than or equal to this divided by that, which is exactly what's. Okay, so that's the Markov or Chebyshev inequality, which we're going to use today. Let's talk about a special case which we're going to use. Suppose we have a random variable and we look at the second centered moment. Let's call that y. So I'm going to apply the inequality with k equals 1 and this random variable, and I get that the expectation of y is the variance of x, so it's the second centered moment, and then whenever a is bigger than 1, I get this. Okay, so that's just a special case k equals 1 of the previous inequality for this particular random variable. Another thing I should say here, which is also trivial, but I guess I should say, I assumed throughout that a is bigger than 1, but I didn't really use that a is bigger than 1 anywhere in the proof. In fact, it's not really important that a is bigger than 1, but this inequality is useless when a is smaller than 1 because this is the probability space. So this number is always at most 1, and this bound becomes trivial. And often, and here also this because of Jensen's inequality. This is also a trivial bound somehow when a is smaller than 1. Okay. So another fact from basic probability that we're going to need today, which I'm sure most of you know, is the Borel-Cantelli lemma. Let me remind you what that is, and also prove it if you don't know what it is. So you have a probability measure. I'm going to write this in the language of measure theory, or not so much probability. If you have a probability measure mu on a space X, and you have a sequence of measurable sets, A1, A2, etc., such that the sum of the measures converges. So the series of measures is summable. Then for almost every x in x, there exists an n0 depending on x, such that for all n bigger than n0, x is not in an. In other words, almost every x participates in only finitely many of these sets, A1, A2, etc. But the number of sets that it belongs to depends on x. So that's the order of quantifiers. So you see that eventually x is not in an, but what eventually means is this: it happens for some time, after some time n0 depends on x. So some x's will belong to, say, 2 or 3 of these ans, some will belong to 1,000,000, but almost every one will only belong to finitely many. Proof. Let's talk about the complementary set. So the set of x's which don't satisfy this condition. So define A infinity to be x and x, so that there are infinitely many n for which x belongs to an. This is the set that we want to prove has measure 0. And you can write this set. So you can write this as the intersection over n, the union, and at least n of the ans. So this is the set of x's such that for all n there exists a larger n where x belongs to an. So it's exactly this set A infinity, and then the measure of A infinity is the limit as n goes to infinity of the measure of this union, because when you have a decrease, these sets here depend on m, and we're taking their intersection. So this is the measure of a decreasing sequence, and so the measures behave continuously with respect to decreasing sequences of sets. So the measure of A infinity is the limit of the measures of these sets, but by sigma subadditivity, this is less than or equal to the lim as m tends to infinity, sum n goes from n to infinity, mu of an. And this right-hand side is the tail of a convergent series. We assumed that this series converges, and so its tail goes to 0. This is precisely this tail. Okay, so that's the proof of the Borel-Cantelli lemma, which is standard. And that's the kind of the quick crash course on very, very basic things in probability theory. And with this in hand, I want to describe set of results and start talking about their proof. And so the theorem that Rogers proved in a sequence of papers in the 50s, mostly in 55. So there's a famous paper from 55, and there are some other papers in the 50s. He proved the following: if F is in CC, well, in L1. Let's say with compactly supported. F is a compactly supported continuous function on Rn. K is an integer, a positive integer less than n. N is the dimension. Then the Siegel transform F hat belongs to Lk. So in other words, the kth power of F hat is integrable, or in other words, I'll just write that in words, i.e. the raw kth moment of F hat is finite. Moreover, we're going to see Rogers obtained explicit bounds for this kth moment. When I say explicit bounds, what do I actually mean? Let me just remind you. Let's go back to the Markov inequality. I said that, so the kth moment is this thing, is the average of x to the k. And so when I say an explicit bound, what I actually mean is that I'd like this number and this number to be close. The expectation of x to the k should be close to the expectation of x quantity to the k. And that's sort of what I mean by an explicit bound. And you're going to see some examples. So this is what Rogers proved in 55. There are two things here that are interesting. The first is you could ask what happens if k is bigger than n. So in other words, do these functions have higher moments? And the second thing is you notice that in Rogers' treatment, k is an integer, but this question makes sense for k, a real number. So which LP space does F hat belong to for p, not necessarily an integer? So the answer is n is the exact upper bound. So this is a theorem. So I'm writing a reference which might not be the first reference. I know this from a paper of Esker Margulis Moses from 98. Maybe there's an earlier, maybe this was known before. This is not the point of the Esker Margulis Moses paper. Maybe this was known before, but this certainly appears in that paper. So if you have, I'm writing P, not P for a prime, but for LP spaces. So P is a real number, at least one less than N, and F is again compactly supported continuous, then F hat is an LP. And on the other hand, there are functions for which F hat is not in Ln. So the bound on the integrability of this transform is m, the dimension of the space that we live in. So that's the result of Esker Margulis Moses. So I'm going to sketch the proof of this Rogers 55 bound. And you'll see that it's actually not extremely difficult. I think it has an undeserved reputation of being a very difficult result of Rogers from the 50s, but I don't think it's that difficult. But there's some kind of annoying and delicate combinatorial analysis, which I'll sort of show you where it goes, where it gets used. So I'm going to give you a fairly detailed sketch for k equals 2. And then I'll discuss the general case briefly, and you'll see that it's not as bad as you might think. So this is what we want to do. So we will give a sketch of proof of the Rogers bound, which is more detailed for k equals to 2, which is k equals to 2 is actually very, very useful in applications, as we'll see. So let's let k be a integer smaller than n, positive integer, and let's write r to the kn in 2 different ways. So first I want to think of this as k by n matrices, and I also want to, so isomorphic too. And I also want to think of this as k tuples of n-dimensional vectors. Okay, so these are 2 different ways of thinking of the space rk to the n. And let's give a theorem which is independently interesting. This is theorem of Siegel from 45. Well, let's, yeah. So we take a function, which is an L1 function on R to the Kn, with respect to the Lebesgue measure. And let's define one more transform. So I'm going to write a hat with an n and a k next to it. So this is going to be a function on the space of lattices. And the way it's defined you take k tuples of non-zero vectors and you evaluate f on this k tuple. Okay, remember the function f is a function on k tuples of n-dimensional vectors, and so we can sum it on all the k tuples in our lattice, and we take the non-zero vectors, and we call this a transform. So the transform that we had before corresponded to k equals 1. So I'll just write that in the mark. So what we denoted by f hat is just what we're now denoting by f hat n1. And then we have a Siegel summation formula again, the integral of this transform. Again, this is a function now on the space of lattices. This is the Lebesgue measure, the integral of the Lebesgue measure of f. And I want to call this Siegel summation formula 2 with subscript nk. So we had the, this is exactly, if k equals 1, this is exactly what we proved before. So for k equals 1, we recover what I called Siegel summation formula number 2 in last week's lecture. This is a generalization. So this appeared in the same paper of Siegel in which the Siegel summation formula was proved. And the proof is basically the same. I mean, in terms of Siegel's approach, the proof that I gave last week and the week before was not exactly Siegel's proof. It was related to Siegel's proof. The proof that Siegel gives for this formula is essentially identical to the proof that he gave for the original formula. So let's sketch this proof. Of this theorem of Siegel. By r to the n to the kn with subscript li. Li stands for linearly independent. These are the linearly independent k-tuples. My stylus is not wanting to write for some reason. Sorry. Linearly independent. So this is RKN LI. This is an open open dense subset of RKN. In fact, if we think of these k-tuples as matrices, we can think about it as follows. We are taking matrices of size k by n, and we're removing matrices which have all their minors have determinant 0. So determinant minor. This is a k by k minor. Sorry. Zero. So you think of these matrices as being k by n matrices. If the rank is not, if they're not linearly independent, that means the rank of this matrix is less than k, which means that all the minors, the determinants of all the minors of size k vanish. The vanishing of a minor is clearly giving you an open dense condition. So this is an intersection of finitely many open dense subsets, and so it's open and dense. And the theorem, where did it go? The theorem is about functions which are L1 functions on RKN, and we already saw many times that it's enough to prove such theorems for a dense collection, because this is an isometry in L1, and so a dense and L1 collection would be compactly supported functions on this space. So enough to prove this formula for functions which are supported on this, which are supported on a compact set contained in this set of linearly independent k-tuples. Now, SLNR is acting transitively on this collection, right? If I have any k-tuple, k is less than n. So if I have any k-tuple of linearly, any two k-tuples of linearly independent vectors, then there's a matrix which is invertible, and it takes the first k-tuple bijectively onto the second k-tuple. And moreover, since k is less than n, I have some freedom with the what I do to another vector, and the last vector I can rescale so that the determinant can come to 1. So I can always take any k-tuple to any other k-tuple, preserving with determinant 1. And so this is a space on which epsilon acts transitively, and the stabilizer in this group SLNR of the standard k-tuple, the first k vectors of the standard basis, is in matrix form given by a block matrix. Here you have the identity matrix of size k, and here you have zeros. That's because you're mapping E1 to E1, E2 to E2, etc. by linear transformations, and here you have just anything else, as long as the determinant is the determinant of the block down here should be 1 in order for the entire determinant to be equal to 1. So that's the stabilizer group. It's not really important with the stabilizer group. I just mentioned it, so it should be familiar now, because we had this the case k equals 1. We had this group U here where we had a similar computation, and so this space admits a unique SLNR invariant. Right on measure up to scaling, namely the volume measure, the restriction of the volume measure on the Lebesgue measure on R2K. Right? We already know that when you have a group acting transitively on a space, then if there is a radon measure, then it's unique up to scaling. And I just showed you that SLNR is acting transitively. So if there is a measure, it's unique up to scaling.
Bala?
Yeah.
You said that SLNR acts transitively. Doesn't SLNR preserve volumes? And so like we
Yeah,
can't.
so that's what I said a few seconds ago. So k is less than n. Where did this go?
Right.
Assuming that k is less than n. So you can map the first k vectors to any other k vectors, and you still have freedom with the rest of the vectors. So you can rescale the last vector to change the determinant. Make it
okay.
I forgot what I wanted to say. Yeah, so SLNR is acting transitively, and so if a radon measure exists, a non-zero radon measure exists, then it's unique. And we do know that there is an invariant radon measure, namely the Lebesgue measure on Rn is invariant under SLNR. And since this is an open set, its restriction to RKN-Li is non-zero. So this is the unique measure. Okay, so we have the existence and uniqueness of a special measure. Now, let me put a star here. You show that whenever you start with a compact supported continuous function on this space, then you define this generalized Siegel transform. The function that you get is integrable. Okay, so this is something that we won't do, and this is the main part of the proof, the main technical part of the proof. But I'll comment about that now. Well, let me complete the proof and get back to this point at the end of the proof. But so this is something that one has to do. One has to check that when you perform this transform, you get a function which is integrable. And let's assume that for now, and I'll come back to it in a second. So assuming this statement, um, we can look at the following map that sends compactly supported functions on this space to real numbers. It sends a function f to you first transform it into a function on the space of n-dimensional lattices by this transform, and then you integrate that with respect to the R0 measure on the space of lattices. So again, I needed star in order to know that this operation is well defined. Once I have star, and I know that this operation is well defined, this map is a continuous positive linear functional on this space. So defines a Radon measure by the Riesz representation theorem. It defines a Radon measure. Let's just call it mu on this space. And what do we know about this mu? Well, I claim that if I let me write down a claim. So claim for every function and every element of SLNR, if I first compose F with G and then take this transform, that's the same as taking the transform and composing it with G. Okay, G is acting on two spaces. It's acting on this space, and it's also acting on this space. And so since it's acting on this space and acting on this space, it's also acting on functions on this space and functions on this space. And I'm claiming that this mapping is equivariant, and that's just a simple check. So let's just quickly check this. So if we take the left-hand side, so let me try to be fancy here. I'm proving this equality. Let me write it in a different color so you know that I haven't proved it yet. And so if I take the definition of this left-hand side, just by definition, this is the sum over non-zero vectors of the function f composed with g applied to these guys, which is, by the way that SLNR is acting on these k-tuples, this is the sum. I should have written linearly independent here. This is equal to this. That's just the way that SLNR acts. But this is exactly the same if I make a change of variables. Vi equals G of Ui. The Vi's are elements, non-zero linearly independent elements of the lattice G times L. Sorry. So this is exactly the transform of F evaluated at GL. Okay, and so yeah, so maybe let me just to make this a nice proof, this, what I started with is this side for a given function L, and I got the right-hand side for the same given function L. So I proved the claim. I'm going to take just a few extra minutes to finish this discussion before we take a break. So I've proved to you this, this claim. So this proves the claim. So from the claim, it follows that the measure mu that we've defined through this Riesz representation theorem and this formula is going to be an SLNR invariant measure. Why is that? This means that this proves the claim. It follows that mu defined above is SLNR invariant, because for any G in SLNR, the integral this integral is just by definition of mu. Mu is defined by this transform. So this is this. This is the definition. Now we just use the previous claim, and we get this. But the measure, the Harzigel measure is invariant, so this gives this. This is because MKN is SLNR invariant, which is the integral of V. So I've proved to you that mu is SLNR invariant. So by uniqueness, it's actually equal to the volume measure up to a constant. So in other words, what that means is that the integral multiplied by C, or, well, this is C goes to the other side, I guess. This is equal to so this is the formula that I wanted to prove up to the evaluation of the constant T, and to evaluate, so it remains to show C equals 1. For this, use the function f, which is the indicator of BR, where BR is a box. So minus R to the K times N. And we did this as we did for K equals 1. It's not hard to show that for any lattice L, no matter what it is, if you look at F hat, I'm sorry, F should be the indicator of BR divided by the volume of BR. F hat of L, and this is a sequence of functions depending on a parameter R. F hat of L converges pointwise as R tends to infinity to 1. So this is exactly because the number of points that a lattice has in a ball you know what happens to it as the ball gets larger and larger for each lattice. And using the dominated convergence theorem, and here you need to justify that, which I'm not going to do, and plugging into the identity, which I want to call 2 stars, which is this identity, you get that C has to equals 1. So I'm doing this very quickly because we already did exactly this type of argument in the case k equals to 1. So that's how the proof of the Siegel formula goes, and there's only one point which requires work, which we didn't do, which is this point star. I'll just say something about it, and then we'll take a break. Where did star go? Here is star. So there's a whole theory associated with lattices in semi-simple groups, and a large part of that theory was developed by Siegel for exactly this kind of an application. And what Siegel was proving is 2 things. The first thing he proved is that SL and Z is a lattice in SL and R. So I'm reminding you, a lattice in a general Lie group is subgroup, so that there's a fundamental domain for the quotient which has finite measure with respect to Haar measure. And so Siegel proved that SL and Z is a lattice in SL and R, but that's not where you stop. As soon as you've proved that you have a lattice, then compactly supported functions or bounded functions become integrable. But these functions here are not going to be bounded typically on the space of lattices. As when the lattices get short vectors, if F is like the indicator of a ball, when the lattice has a short vector, there are many, many points inside the ball, and this counting function explodes. So you have to do an analysis of what happens to lattices with short vectors and how what measure is given to these. And that's a whole subject called reduction theory, which was developed by Siegel. And using this kind of analysis, you can decide which functions decay rapidly enough so that they're integrable on this space. So this is kind of a non-trivial part of the whole discussion that we're not doing, but sort of once you have it, the rest sort of follows very, very cleanly. Okay, any questions before we take a break? All right, good. So let's take a 10-minute break and then continue. Okay, let me continue. So, can you hear me? Yes, Manuel, I can see you, Manuel. So let's remind ourselves what we've proved so far and what we want to discuss. So we want to discuss the kth moments of the Siegel transform. And so those are, we have here an F hat depending on K. Oops. We have this formula here, which is a different transform for each K. And what we'd like to know is that if you let K equal to 1, which makes this the usual transform that we had before, you get a function whose kth power is integrable. So I just wanted to say that we've basically shown this from the theorem, from this Siegel theorem, but we also want bounds for the integral of the kth, for the raw kth moment. So let me first explain why this statement shows that the original f hat is in LK. So let's write that as a corollary. For f in L1 Rn, f hat, which again is defined in the usual way, sum over all zero lattice points, is in LK on the space of lattices for all k less, for all integers k less than n. And the reason is, given f, define, I'm kind of running out of letters, so given given f, which is here, define f1 here, L1 of Rn and L1 of R to the Kn are all both respect to Lebesgue measure by the value of f1 on a k tuple is the product of the original f on those k elements. Now, the fact that f is integrable with respect to Lebesgue measure on Rn means that by repeated integration, f1 is also integral on Rn to the k. So this kind of a mapping, f1 is certainly in R to the kn integrable. And the summation formula, so the integral of f hat quantity to the k on the space of lattices. We want to show that this object is finite. This is nothing but the sum of non-zero vectors of fu, this thing to the k. When you open this kth power, you're multiplying this object by itself k times. So each element of this sum meets every other element of this sum. And so you get a repeated sum. So this looks like the integral over the sum. And here you're just taking k tuples of non-zero vectors, and you're multiplying them. That's just what the kth power is. But that's nothing but, this is nothing but the transform of f1. This formula in here is the function f1 evaluated on u1 up to, yeah, maybe I'll do that in the next step. So this is the integral of the sum we get this. And by the Siegel formula, the Siegel theorem that we just had, this is by. Okay, so the fact that f hat is k times integrable just follows from the previous formula, very simply by change of, by this definition of the function f1. But now we want, so this proves the corollary, we want bounds on the so-called raw case moment of f hat. And let me first discuss the case k equals 2, so the second moment. So this is the so-called, this is the famous theorem of Rogers. This is called the Rogers second moment bound in the same paper that I mentioned earlier from 1955. And it says the following. So for every f compact is supported on Rn, again, the usual transform which is now a function on the space of lattices, satisfies that the variance of f hat, which I'm reminding you is just by definition the is this thing. This variance is bounded from above by 2 times the sup norm of f times the L1 norm of f hat. The L1 norm of f hat is the same as the L1 norm of f by the standard Ziegler summation formula. Okay, so what are we doing? We're getting a bound for the variance, which is the second moment, in terms of a constant times the sup norm of f times the first moment. Okay, so this is the bound. This is a very useful bound. You'll see in a moment why it's so useful. It's already giving you some kind of concentration for the values of these random variables given by the Ziegler summation formula close to their mean. Let's prove this. And after the proof, I'll go back to discussing why this is so useful. So first of all, just remind you of the formula from probability. The variance of x is the expectation of x minus the expectation of x quantity squared. So it's the eccentric second moment. And if you open up this square by the just by the binomial theorem, and you remember that expectation, which is integration, is a linear operation, you get that this is the same as the expectation of x squared minus the expectation of x quantity squared. Okay, so I'm not writing it down. This is kind of a trivial formula from probability that you can check for yourself. So we're going to use this. So in order to compute this, we're going to first compute this guy and then sort of subtract off this guy. So let's compute this guy where instead of x, we have f hat. So we will compute. So in other words, we're going to compute the raw second moment. So this is what we want to compute, and we're going to do it using the Ziegler summation formula, which I called the Ziegler summation formula 2 dot nk with k equals to 2. So there's a constant here, 2 in front. I'm going to separate f into its negative parts and positive parts. So, and I'm claiming that it's enough to prove this separately for the negative and positive parts if I manage to prove it without the constant 2. So we will write I'm going to for some reason my stylus is misbehaving today. So I'm separating f into its positive and negative parts, and I'll just write it this way. So I'm assuming that f is non-negative. I'll say more about, I'll justify this more carefully in a second. And so let's first work under the assumption that f is non-zero. So this means that also f hat is also non-zero because the transform is order preserving. And let's define f1 of xy to be f of x, f of y, as we did in the previous proof. f1 is a function on two n variables. And so the object that we want to compute, as in the previous proof, is, okay, let me write this out in complete detail one more time. Thinking that I may have just lied to you at the end of the previous lecture. Let me just check this stuff. Yeah, I think I did lie to you at the end of the previous lecture, right? So sorry, at the beginning of this lecture, the proof of this corollary, I'm sorry. So it's not good to start off the new year with a lie. So let me tell you where, can anyone see where the lie is here? What's the mistake that I made in this statement?
They need not all simultaneously be non-zero, right?
True. They're all, no. This is
no.
all simultaneously non-zero, but there's something else. So in the Siegel formula that I used, where did it go? Where is the Siegel formula? Siegel's theorem. What's the lie? There was something about linearly independent sort of disappearing. So here we had a transform that did not involve linear independence. So we just took all the k tuples and summed them up. And maybe I didn't lie to you. That's confident. Let me think for a little bit. All right. Yeah, okay. I didn't lie. That's what I like to. For some reason, something is confusing me. We'll see that we might see where the confusion shows up in a second. So this is the quantity that I want to estimate, and I'd like to break this up into two pieces. The cases where U and V are linearly independent, and the cases where U and V are not linearly independent. And yeah. sort of seems pointless to go on if I'm, okay, let's stop the recording and take 5 minutes because there's something that I'm doing that is wrong and I can't figure it out. So I'm going to take 5 minutes to think and we'll continue. So let's continue in 5 minutes. All right, so I still have an issue that I haven't really resolved, but I'll explain to you where the issue is. I'm having a hard time seeing my screen. So you can all hear me, right? All right, so and is my screen shared? I guess my screen is not shared. Okay, that's the issue. Let's share my screen. So the issue was the following, and I still haven't really understood where the mistake in my proof was. The definition of the transform in k dimensions, one needs to, in order to get this formula here, this Siegel summation formula number 2, one needs to sum over linearly independent k tuples. So let's add linearly independent to the definition of the transform. Let's think about the proof for a moment. Maybe as we go along, we can find the mistake, and maybe we can't. We'll see. So we define the transform in this way, and we first start with functions which are compactly supported, and their support lies in the set of linearly independent k-tuples. So for functions which are 0, where you have linear dependencies between the vectors, this expression will not change if I add linear independence, in other words, reduce the number of k-tuples, or not, because what will happen is that f evaluated at the case where you have linear dependencies will be 0 anyway, because it's supported outside that set. Okay, so the two transforms that I defining, the one written down and the one that was written down before, they're exactly the same on this set, on k-tuples living inside this set. Okay, and so then, well, the proof of the Siegel transform for functions supported on this set sort of proceeds in exactly the same way. The issue is, I guess, when you want to extend this to k-tuples which don't satisfy this equation. And I just wrote down that since what I said verbally, I guess I didn't even write it down. What I said verbally was, well, these compactly supported functions in this space are actually dense in L1 of Rkn. And I stand by that statement. I think that statement is correct. But then I said that it's sort of obvious that the transform, that the formula here extends. And my notes say that what extends is when you make the definition assuming linearly independence. And when you make the definition where you remove the word linear independence, the formula does not extend. Okay, so let's leave it at that. With that, the sketch, the statement now, I've changed the statement. This is the statement. I'm keeping the sketch of proof, although I'm not completely clear on where I used this condition. I think I used it here in the approximation argument that says that these functions are sufficient for proving it in general. And now here's the place where I cheated you with less scruples. That's in the proof of this corollary. In the proof of this corollary, I started with this expression. Then I opened up the kth power. And what I naturally got was k-tuples of functions which are non-zero, k-tuples of non-zero vectors, but they're not linearly independent. There's no reason for them to be linearly independent. But nevertheless, I used the formula that I had before when moving from this line to this line, although this is not the same, the right-hand side, this transform is not the what's written on the left-hand side because there's the condition of linear independence does not appear. So let's just mark this with a red color, and let's just put a warning sign on the corollary, and then in the notes, I'll try to put more order into these notes and make this more correct. Okay, so this is where we now stand. We're ignoring the corollary, and we're moving on to k plus 2. And we want to discuss this statement. So let's just add to the statement that f hat is an L2. And we have this bound. Okay, so this is what I want to discuss the proof of this. All right. So same issue. I opened up the meaning of f hat. I wrote down the meaning of f hat, and then I'm going to open up this product. And when I do that, two terms are going to appear. I'm going to get f of u times f of v when u and v are a pair of linearly independent vectors, and when there are linear dependencies. So here's what we get. Let's just write it out. So I'm separating the sum into two pieces. And the first piece, the functions are linearly independent. And then I can use the formula that I had before, the Ziegler summation formula number 2. So let me just write this first guy out as this. And let's make this into an upper bound. And let's pull out one of the values of f here. We have products of functions f of u times f of v. F is a bounded function. I'm just going to upper bound. Remember, everything here, all the function here is non-negative. I'm just going to upper bound this integral by pulling this fu out and replacing it by the sum of, by the sup of the now I'm making another mistake, I'm afraid. I'm sorry. Okay, there's going to be another mistake coming soon, so I'll just try to avoid this. Let me think for a moment. Okay, let me try to do this correctly, but my notes are incorrect. I'll try to write this out correctly. So if u and v, so let's hold off with this for a second. If u and v are linearly dependent and they both live in a lattice, that means that they're both products of a certain primitive vector, the same primitive vector, by some non-zero numbers. So let's write this right-hand term that appears here in the following way. So I'm going to take a sum. W is a vector of L, which is primitive. And K1 and K2 are integers, K1 non-zero integers, and let's say K1 is positive. And here I'll write K1 W, K2 W, integral of this okay. So again, what have I done? I'm interested in the case where I have two lattice vectors and they're linearly dependent. In linearly dependent, two vectors, non-zero vectors being linearly dependent means that they're on the same line. They're on the same line and they belong to the lattice. So that means that there's a primitive vector on that line and both of them are products of that primitive vector. So the primitive vectors are being called W, and now all possible cases, I choose that primitive vector such that U is a positive multiple of that primitive vector. And then V might also be a positive multiple of that primitive vector, or it might be a negative multiple of that primitive vector. So that's why we have K1 positive, K2 is just some non-zero integer. So that's the formula that we get when we split up the integral into two pieces. And I guess this is still, at this point, still an equality. Okay, so now I'm going to treat these two terms separately. The first term in this sum, so this term here, by the Siegel summation formula that whose proof we sketched before. So this is Siegel summation formula 2 comma n. This is the integral of, I'm sorry, this says f, and it should say f1. Remember, f1 is this function. So that's f1 with respect to the volume measure on two n-dimensional space. And this formula here, I'd like to upper bound by pulling out, replacing one of these elements by the sup norm of f. So what I get looks like this. So I'm going to get a lower bound here, and here I'm going to get the sup norm of f, and here I'm going to get the integral of the sum k in n, and the sum WL primitive f of kw. Okay, so I've pulled out this guy out of the formula and replaced it by the sup norm of f, giving me an upper bound. Okay, both of these terms have a separate life. So f1, the integral of f1 on two n-dimensional space is exactly the integral of f on n-dimensional space squared. That's because f1 is given by this formula, and I can do Fubini. And here, let's pull the sum out. And this is something that we already had. This is the primitive transform. So this is the integral of over the space of lattices of a transform. I'll write it all out and explain. So there's a P here, and there's an L here. And where fk of x is fk. Echo.
Yes.
Question? Was there a question? Do you want to write it in the chat maybe, or try again?
Should work now.
Yeah, okay.
I think in the previous line, it should be the sum over, when you bounded the sum over f of k1, k2, it should be the absolute value of f of kw. Right? Because
Sorry, say that again.
in the first line here, you have the sup norm of f times the integral of the sum over k over w. That should be the absolute value of f of kw, not just f of kw.
F is non-zero. F is non-negative.
Oh, we're assuming that f is not
Yeah,
negative?
yeah. I've assumed I separated into positive, negative parts, and I assume that F is non-negative.
Oh, okay. Sorry. Thanks.
Yeah. Um, something is wrong again. Oh no, it's okay. Okay, let me continue, although, yeah, I might have to backtrack. So remember that we had a transform with a P on the right-hand side. So we had a definition with this P here, and this is the transform where you sum over primitive vectors. And for that transform, we also had a Ziegler summation formula, which we called the Ziegler summation formula number 1. And so here we're getting this. And here we're getting the sup norm of f and the sum k and n, and we're getting this we're getting the integral of fk on Rn multiplied by a constant. So this is zeta n integral Rn fk. So this is something that we called Ziegler summation formula number 1. And now I'm going to pull out the integral. I'm going to pull out zeta n, and I'm going to pull out the integral of f with respect of the original f with respect to Haar measure. And then in this integral, which is an integral with respect to Rn, I'm making a change of variables. X maps to k times x. So this gives me a Jacobian of 1 over k to the n. This should have been a zeta n inverse here, I think. Zeta n is bigger than 1, and we're doing an integral over a sparser set, so we should get a smaller number. Just checking myself here. Right. And so putting everything together, we get these are two zeta n's, they cancel, and we get this. Okay, now I'm afraid I think, let's not scrutinize this too carefully because I think I may have cheated you. So there's this famous saying in mathematics that the teacher can make mistakes as long as the teacher makes an even number of mistakes. So I think I may have made an even number of mistakes leading to the correct statement with an incorrect proof. Let's not look at this too carefully because we're sort of running low on time. I'll try to fix things in the notes, and if they really require further discussion, we'll do that next week. But what have we gotten? We've gotten the statement under the assumption that f was non-negative, because this is we're integrating. Sorry, we're integrating this thing in order to get the variance. We need to subtract this thing, which is the integral of f squared. And so this minus this, which is the expectation squared, is this. I'm sorry, is this. And that's exactly what we want. Okay? Now, the only difference is that we assumed that f is non-negative, and we had this formula 2. And now if you do this twice, once for the negative part and once for the positive part, you can see that this constant of 2 accounts for splitting the function f into positive and negative parts. So let me write all that down. Move it. It's not the end of the proof. Subtracting with the integral of f hat, which is the same as the integral of f for both squared. For both sides, and replacing 1 by 2 to account for both f plus and f minus, get the conclusion. Okay, I'm sorry. So like I said, there might be mistakes here. I'm having a confusion that I don't want to discuss with you because it will only confuse all of us more, but I'll try to fix it in the notes. Okay, so this achieves both goals of the argument achieves both goals. In other words, it shows both. So there's kind of an induction going on. The induction, let me just say the general idea, and you'll see the complication in higher dimensions. So the general idea is the following. You take the function f hat, you take its second power. In the general case, we're going to be taking f hat and taking its kth power. The form that takes already appeared in the corollary, in the proof of the corollary. We take this, we take its kth power, we open it up, and we get sums of this type. The sums of this type split up into two kinds. There's the kinds where the UIs are linearly independent. For those, we have a Siegel summation formula, and they give us the main term. So this gives us a positive number, and it's the main term. And then we have linear dependencies. When we have linear dependencies between these, we can express some of them as combinations of the others. And then we reduce the dimension by 1, and we reduce the number of k-tuples by 1. And that's exactly what we did in dealing with this linearly dependent part. We expressed it in terms of primitive vectors and pulled out one of these terms, just replacing it by its sup norm. And so then we can run an argument by induction. In the case k equals 2, this argument is not too bad. In the case k is bigger than 2, there are various kinds of linear dependencies depending on the rank of the k-tuple, and it just becomes more complicated, much more complicated, in fact. And that's sort of the bulk of what Rogers did, and that's why his work has a reputation of being extremely complicated. So there's a kind of a combinatorial discussion that needs to be done regarding how you deal with linear combinations, what's the rank of the relevant k-tuples. And not only is the analysis more complicated, but so are the statements. I'm not telling you the statements of the Rogers formulas for higher moments, just because the statements are fairly complicated and they're spread out over several papers. Okay, so we have this Rogers second moment bound, and let's take a break. I'm going to, after the break, I'll give you an application and show you why this is such a useful thing to have. So let's take 10 minutes break. All right, let me continue. So I'm going to apply the Rogers second moment bound to solve a certain counting problem following a famous paper of Wolfgang Schmidt from the 60s. So let me state the result. And I guess I was hoping to prove it all today, but I think I won't have time, so we'll see. So let's recall, so application to counting lattice points. And growing sets. Following Schmidt. From 1960. So recall we had an exercise. This is exercise 3 on your exercise sheet. This is sometimes known as the Gauss circle problem, but it's actually a kind of a general fact. Take any lattice of covolume 1, any bounded convex set S with non-empty interior. And we're trying to count the number of elements that the lattice has with R times S. R is the parameter. R times S is the dilation of S by factor R. And in the exercise sheet, you were asked to prove, and this is not very hard, that the number of lattice points in this dilation as R goes to infinity behaves like this. The main term is the volume of the body, and there's an error term, and the error term is growing like constant times R to the n minus 1. As R goes to infinity, where the implicit constant depends on L and on S. Okay? And so this, we could call this guy here the main term, because it's growing essentially like R to the power n. It's the volume of S times R to the power n. And this is the error term. And let's rewrite this in another way. So this is the main term, and the error term looks like the main term. Oops. Looks like the main term to a power smaller than 1. So this is to the power 1 minus 1 over n. That's not a hard theorem to prove. In fact, I'm hoping that most of you know how the proof goes. And the question
is the implicit constant in the second formulation independent of S?
Dependent. It's the same formulation. I'm just rewriting it. I'm saying that R to the n is the volume of R to the S times, sorry, the volume of R times S is the volume of S times R to the n. Right?
Yes.
And so R to the n minus 1 is exactly this thing with a constant, which is basically the volume of S to some power. And so the constant here does depend on S.
So in this formulation, it still does depend on S.
Yeah, in both formulations, it depends on S.
Okay. Okay.
Question, can the error term be improved? And if so, for which choices of L, for which choices of S, and maybe for more general sequences of growing bodies. Right here, the asymptotic we're taking is when we take a fixed body, say a ball, and we are increasing the volume of the ball or the radius of the ball by multiplying by a dilation. You might care about other sequences of bodies which grow at a certain rate, not necessarily one body which is being uniformly inflated, but some other thing, some other way of getting bigger and bigger sets. So this is sort of a general question. So this is a classical question. I don't want to write down the history of related questions right now because I'm running low on time, but maybe I'll say something about that next week. And now I'll just formulate one conjecture and then write down the theorem that we're going to be proving. Conjecture, this is a conjecture of Gutze from 1998. It's about almost every lattice with respect to the Harzegel measure. So for almost every lattice in Rn, and for S being the Euclidean ball, the number of points in R times S is the volume plus an error term which looks like this. Oh, I'm sorry, I should have an epsilon here for all epsilon. So this is Goetz's conjecture. Let me, before saying what the implicit constants depend on, let me rewrite it again as the, in terms of the volume. So the main term is the volume, and then the error term is the main term to a power, and the power is 1/2 minus 1 over 2n plus epsilon, where the implicit constant depends on L, depends on S, and depends on epsilon. So this is the conjecture. Let's compare the conjecture to what we already know. So we know 1 minus 1 over n. This is called the power savings. The main term is the power is 1, and then in the error there's a power savings, and in the what we know from easy principles, we get 1 minus 1 over n, and we know this for every lattice and for every growing set, convex set S, and gets us conjecture for the Euclidean ball, a much better power saving, smaller than 1/2, 1/2 minus 1 over 2 minus 1 over 2n. So that's the conjecture, still open. And the theorem that we're going to be proving is almost reaching this for even a greater, for even more general growing sets than just the Euclidean balls. So let me make some definitions. So our sets are going to be called omega. So omega R for R positive is a collection of Borel sets. We're going to call it an unbounded ordered family. If it satisfies the following conditions, Ordered means that these sets are nested. So the bigger the parameter, the set corresponding to a bigger parameter contains a set corresponding to a smaller parameter for every choice of the parameters. The volumes of each of these sets are finite, but they tend to infinity as the parameter tends to infinity. And finally, they vary continuously. So they increase continuously. In other words, for every phi, there exists an R such that the volume of omega R is equal to V. So the volumes don't have, there's no jump in the values taken by these sets. So examples here could be ball radius R. You could take a set S in Rn of infinite measure and define omega R to be the intersection of S with the ball radius R. So, I'll just draw a picture. So here we are in R2. And we have maybe some kind of crazy looking set with infinite measure. That's this red set. And the parameter is measuring the volume of the ball. So this would be the first set. This would be omega 1. Maybe this would be omega 3, would be everything that's in here, etc. I hope I made this more or less clear. It's any collection that grows with the parameter, and it doesn't have to fill up space in any way. It just has to grow and acquire infinite volume. So that's the notion of an unbounded ordered family. And then with this notion, Schmidt in 1960 proved the following theorem. So let omega R be an unbounded ordered family. In Rn. Then for every positive epsilon, for almost every, with respect to the Harzigel measure, for almost every lattice, we have the following growth. The number of points in omega R looks like the main term, which is the volume. And then there's the power of the volume. And the power is 1/2 plus epsilon, where again, the implicit constant in the O notation depends on L and on epsilon. So this is Schmidt's theorem. It's a very general theorem in terms of the collection of bodies. It's any increased unbounded ordered family, so that's a huge possibility. One case are these balls, is a possible case. And in the case of balls, if you compare to the conjecture, the conjecture says that the power should be 1/2 minus 1/2n plus epsilon, and Schmidt gets 1/2 plus epsilon. So Schmidt is coming quite close to the conjecture. And he's not using any particular features of the sets. So in particular, he's not using any symmetries that the Euclidean balls might have. And his result is the best known result towards the conjecture. There is no better result for Euclidean balls. So remark, Schmidt's result is not obtain the bound 1/2 minus 1/n plus epsilon in the conjecture, but it's the best result. No. Okay, so and the proof of this theorem basically involves the Rogers second moment bound. So let's start with the proof. I'm not sure how much I'll be able to, how much of the proof I'll have time for. Proceed to the question. No.
Just to
Yeah.
be sure, the constant here is independent of the family.
No. It depends on the family.
Okay.
So, yeah. Okay, so let's prove this. So for the proof, we will need some lemmas, notations. In the definition of an unbounded ordered family, the volume is growing, but you don't know how quickly this volume grows. And it's growing in a continuous way. So in other words, every volume is attained. That's axiom 3 of what it means to be an unbounded ordered family. So I'm going to somehow reparameterize the sets omega r so that they depend on an integer, a natural number, not a real number. And the nth body, I want it to have volume n. And I know that I can do that by axiom number 3. So by 3, for each n a positive integer, there exists omega, there exists an Rn so that the set, which I want to call Sn, which is omega at the parameter Rn, satisfies that its volume is n. So I'm just changing notation a little bit so that I have a control of the growth of the volume. It's just growing with the same as the parameter. And I'm taking integer value parameters. And now let's look at the indicator function of these SNs. So let rho n be the indicator function of Sn. So these are functions in L1. And for two numbers, n1 less than n2, I'm going to have this fancy notation. Rho with n1 on the left, n2 on the right is the difference of these two indicator functions. Which means it's the indicator of the big set subtract the small set. Remember, the sets are nested. So when n1 is less than n2, Sn1 is contained in Sn2. So the difference in the indicator function is 1 exactly on the difference set. So this is because sets are nested. Okay, so let's define our lemma. This is a very useful trick called dyadic decomposition. So let t be an integer parameter, and let kt, I'm defining a set of pairs of integers. So n1 is less than n2. These numbers are integers. They're bounded above by 2 to the t. And I want that that n1 is divisible by some power of 2, and n2 is n1 plus this power of 2. Okay, so let me first take a lemma, and then I'll give some examples of what these pairs of numbers are and why this dyadic decomposition is useful. Then the sum over pairs of numbers n1 and n2 and k2 of the variance of the Siegel transform of this function rho evaluated n1 and n2 is less than 2 times t plus 1 t to the t. Okay, so it's a bound on the variance of a finite collection of functions, of these functions, the Siegel transforms of these sets. And the finite collection is given by this dyadic decomposition. So let me give you some examples of this dyadic decomposition before we give the proof. Suppose t is 4, say. So 2 to the t here, 2 to the t here is 16. I'm sorry, little t can also be 0. Let me move this. So if t equals 4, I go over all the possible little t's that appear here. And the biggest one is 4, and the smallest one is 0. So let's start with 4. So if little t is 4, I can take n1 to be 0 and n2 to be 2 to the t, and they satisfy everything that's in the statement. And that's the only possibility. So, see, the numbers are between, in this case, between 0 and 16, and 2 to the 4th is 16. So the only possible choices satisfying this are these two numbers. If t is 3, then 2 to the t is 8, and I have two choices. n1 is 0, n2 is 8, n1 is 8, n2 is 16. If t is 2, n1, n2 could be any of the following pairs. I can take 0, 4, 4, 8, 8, 12, 12, 12, 16, etc. And the case t equals 0, I get all pairs k plus 1, where k is between 0 and 15. All right, so this is the set kt that appears in this lemma. The proof of this lemma is essentially the Rogers second moment bound. Let's prove it. Just making sure I haven't forgotten anything here. So the variance of this function by the Rogers second moment bound is 2 times the sup norm of the original function, rho, times the integral over the space of lattices of the transform. Okay, so there's a tiny lie here again, but this is kind of an intentional lie. So the lie is that in the Siegel formula, which is, sorry, in the Rogers formula, which is what we did in the previous lecture, where did this go? Yeah, we're using this Rogers second moment bound. In this Rogers second moment bound, I assume that the function was continuous. And now I'm applying the same argument, the same bound to a function which is not continuous, but it's the difference of, it's the indicator function of a certain annulus type thing. So you can move from the continuous functions to the annulus by some approximation argument. All of the quantities in this inequality will change continuously, and you will get this for row n1, n2. So let me just write that down. Note row n1, n2, not continuous, can derive from the Rogers second moment bound and an approximation argument. Other than that, this inequality that is written down here is exactly the Rogers second moment bound. And let's maybe move this remark further down a little bit and add a few lines to this inequality. And so this quantity that you're seeing here is equal to the following. So the sup norm of this indicator function is 1. This is 1. And so this is 2 times the integral. The integral of this guy is the measure of this annulus. So let's write that down. So this is the volume. It's the volume of these. It's the n1 row, n2 is the indicator of an annulus. So this is its volume. And we chose the volume of the nth body to be n, and so we get 2 times n2 minus n1. And let's call this formula 1. Okay. Now let's add up just the number of elements in KT. We're trying to prove this inequality here. Let's sum up the inequality that we got over all possible elements n1 and 2 in KT. And so each value of the difference n2 minus n1 is equal to some number 2 to the t for some choice of t between 0 and capital T. And it occurs 2 to the power t capital T minus t times, and therefore formula 2, the sum n1 n2 in KT of n2 minus n1 is this. So that's just a fact about the structure of these sets KT, which come from the dyadic decomposition. And so I'm summing the inequality number 1 over all possible choices of n1 and 2, and I get that this is bounded by that, and so we get this. 2 comes from line number 1. So this gives, so plug in 2 into 1 gives, or 1 into 2. Okay, combining 1 and 2 gives the conclusion of the lemma. And we've proved the lemma. Second lemma. But notice that we used the Rogers second moment bound. Second lemma. Let's fix a positive number epsilon. Then for every choice of integer t, so the integers, I'm using two symbols for integers. One is capital T and one is capital N. What's going to happen later is that the capital N's are going to be grouped into intervals between successive powers of 2. So in other words, I'm going to look at the capital N's between 1 and 2, 2 and 4, 4 and 8, etc. And the capital T are parameterizing the intervals of powers of 2. So that's the reason for this extra letter. So for every T, there's a set, which I want to call the bad set. Bad T is a subset of the space of lattices, whose measure is bounded above, satisfies the following bound. Such that for every n, integer n bounded above by 2 with t, and every lattice L, which is not in the bad set, I get the following bound, which I want to call formula 3. The value of the transform of the indicator function rho n on the lattice L minus n squared is bounded above by t times t plus 1 times t through t times log 2 t minus 1 to the power 1 plus epsilon. So I'm getting a bound on how far the number, this is the number of points that L has in a certain set, and that set has volume n. So you're expected to have n points, and this is giving you that this holds up to an error, and this is the error. Okay, this is the Markov inequality. Essentially, I think what I'll do is, if I have time, I'll go back to this. Let me skip it for now and continue the proof of the theorem, assuming lemma 2, and then come back to lemma 2 depending on time. Okay, let's do that. And so, proof of the theorem, assuming lemma 2. Let's look at the sum of these numbers. Log 2 is a constant. Log 2 times t minus 1, summation over integer t to the power 1 plus epsilon is a convergent series. And so, and in the lemma, we bounded the volume of the set bad t by this number. So the sums of these volumes where t ranges over the integers is finite. So we can use Borel-Cantelli. And so by Borel-Cantelli, for almost every L, the resistance of T0, depending on L, such that for every T bigger than this T0, for every, L does not belong to this bad set. So let's take n bigger than n0, where n0 is 2 to the t0. And let's take t so that the scale of n is log base 2 of t. So in other words, we want this. So we're choosing t so that it records the scale of n in terms of logarithmic scale. And let's now use lemma 2. And we're going to get a formula that I want to call formula 4. So the bound that I've just written is exactly what lemma 2 gives you. So it gives you that when L is not in the bad set, then it satisfies this bound. Okay, but this is the left hand side is in terms of n, the right hand side is in terms of t. So now I'd like to rewrite this in terms of n, and what this gives is the following thing. T is approximately log n. So from this we get log n squared, and 2 to the t is approximately n. So up to constants, this is O of n times log n squared, and the denominator is log n to the power 1 plus epsilon. And the annoying constant log 2 here, which we carried around, is exactly so that we can say this. And now we've sort of, this formula is almost what we want for the sets Sn, which have volume n. And so now I'd like to show you why, and also sort of interpolate for every set omega r in this ordered family. So for any r, omega r is a set in our ordered family. Let's let n be such that n is an integer, positive integer, and the volume of omega r is between n and n plus 1. And let's let R1 and R2 be such the volume of omega R1 is n, and the volume of omega R2 is n plus 1. So we have omega R1 is containing omega R, is containing omega R2. And so this, we want to call this guy Sn, and this guy Sn plus 1. That's consistent with our earlier notations. And so we get a formula number 5. I'll write it down and then I'll justify it. The number of points that omega R1 has inside L, subtracting n plus 1, this is smaller than or equal to the number of points that omega R has in the lattice L minus the volume omega R, and this is less than or equal to the number of points that Sn plus 1 has in the lattice L minus n. So why is this true? I'm taking this quantity and I'm increasing it by replacing R1 with R. So when I make this set larger, the number of lattice points only grows. So this is replaced by that, and we've only increased it. On the other hand, R is between, the volume of omega R is between n and n plus 1. So if I replace n plus 1 has a minus sign in front. So I replace n plus 1 with the volume of omega R, I'm also making things larger. And similarly in the other direction. So I just use the opposite inequalities in the other direction. So what I'm doing is I'm sandwiching this quantity, which is the quantity that I want to say is small, by the corresponding quantities for the set Sn with the approximation corresponding to n plus 1. And here's the set Sn plus 1 with the approximation corresponding to the set n. Okay? But the point is, if you look at formula 4, this is the, where did this go? Yeah, this is the, if you take a square root of 4, this is the absolute value of this is the number of points in the set Sn minus the expected value, taking a square root. I get square root of n, log n, and log n to the half plus epsilon. So if I take, let's write that down. So taking square root in 4, both sides of 5 are up to constants, n to the 1/2 plus epsilon. So that means that this thing okay, that I have this inequality, and the opposite inequality is proved in a similar way. Similar way means the opposite inequality, I just take the difference between these two, I take the volume of omega r minus the number of points, so I reverse this quantity, and then I replace the roles of R1 and this would be R2, this would be N, this would be N, and this would be N plus 1. All right, so I've proved the theorem. This is what I wanted. I wanted this difference to be, I wanted the growth of the number of, the discrepancy between the volume of omega r and the number of lattice points in it to grow like the volume to the power 1/2, and that's what I've gotten. So this proves the theorem. Quadrilateral lemma. I still have 5 minutes, and I can give you the proof of lemma 2. So let's take another look at lemma 2. So I'm trying to find a set with an upper bound on its measure. This is the set, and every lattice which is not in the set, I want it to satisfy this inequality 3. So I'm just going to define the set so that this inequality holds easily, and then apply the Markov inequality. So proof of lemma 2. The lattices in the bad set T, with parameter T are those for which, if I sum the actual value of this Siegel transform and subtract the expected value and square the whole object. So this is just like the definition of the second, it's a deviation of the lattice from its average squared. So this is, if I were to take the expectation of this, I'd get the variance. So I want this thing to be larger than expected, where the threshold that I care about is this. I don't know why my stylus is misbehaving. Okay, so this is my definition of the set that T. Let's let.
I have a quick question.
Oh.
Sorry. I am confused. In Formula 4, you have a negative exponent at the 1 plus epsilon, right?
But this is a log. So I'm going to be taking the square root. I'm going to kill this with. So
I'm talking about the central term, the log 2t minus 1.
Yes.
And now you're using the positive exponent. You also formulated lemma 2, I think, using a 1 plus epsilon. No?
I don't understand what the issue is exactly.
Can you go to lemma 2?
Yeah. There's a positive exponent in the definition of the threshold of the inequality, and there's a negative exponent in the definition of the measure.
So when you applied it in Formula 4, you used it with a negative exponent.
I don't think so. Let's check. Okay, I'm kind of surprised because it won't affect things, right? But I guess you're right. I mean, if I put in a minus here, it won't affect the proof. I'm kind of surprised, I have to say. Because I'm going to get a log to the power 3. I'm not expecting a log to the power 3, but it doesn't matter somehow. The main term is this term. So what I care about is for this whole object to be taking square roots. This should be the square root of n to the times n to the power epsilon.
Yeah,
So,
okay.
But I guess you're right.
Yeah, it's just because it came up now again.
Yeah.
I was confused.
Okay, so I guess it doesn't make sense to, two things don't make sense. It doesn't make sense to do this proof now because we only have 1 minute, and it really doesn't make sense to return to this proof next week. I'll just write them in the notes. This proof is, okay, actually, no, sorry. This proof does contain an interesting idea, which is this dyadic decomposition idea. So let me do this proof next week again. So I'll just write to be continued here, and then we'll go back to it next week. Briefly, those of you who want to help me out and also amuse themselves are welcome to try and figure out where exactly I was lying, or was I lying? I think I was lying somewhat in the proof of the Rogers moment bound. At least I'm now slightly confused. And yeah, but that'll be fixed in the notes. And if it's notes discussion, then if it's a serious issue, then we'll discuss it next week. All right, so if there are no questions, are there any questions? Okay, so we'll see you next week.
Thanks.
להתראות, תודה.
ביי, ניתן.
תודה רבה.
בבקשה.
תודה.
בבקשה.